All right, so let's jump right in. Good morning, good evening, good afternoon to you all. Welcome to the next episode of the YugabyteDB Friday Tech Talk from engineers for engineers. And I have with me today Krishna Sunder. He's joining us from Washington area, Seattle area. And over to you, Hari. Would love for you to start by introducing yourself, and then you can jump right into the topic.
Sure. Thanks, Kannan. I'm Krishna. Hey, hi. I work in Yugabyte at the TST team, and I mainly work on the control side part of the database, which is master the load balancing, placement, affinity, X cluster, all of those fun stuff. Before Yugabyte, I used to be in Microsoft Azure SQL DB for 5 years, and I owned logging, recovery, leaders, failables, that sort of stuff. And in Synapse DW for 5 more years, working on the OL AP side of the world. And yeah.
So database journey all along?
Yeah, 10 years of databases.
Awesome.
It's fun, right? It's always fun.
Yeah, go ahead, Hari.
Cool. I'll get started with the presentation. Today we're going to talk about using preferred regions in YugabyteDB. Before I get to preferred regions, I'll briefly go over Yugabyte's architecture. So Yugabyte is has a layered architecture. We have a stateless YSQL layer, a query layer at the top.
Hari, did you mean to share the slides or?
Oh, sorry.
No worries.
Can you see my screen?
Yep.
Okay, good. Like I was saying, Yugabyte is made up of the layered architecture. We have a YSQL layer at the top, and it's a pluggable API with Postgres Cassandra. And below that, we have the DocDB transactional layer, which uses RocksDB, Raft, and a custom transaction layer to do all the storage and transaction management. And all the tables in Yugabyte are automatically sharded into tablets. And each tablet is a Raft group. And we use Raft for leader selection and log replication. In this example here, I have 3 nodes, 3 tablets, 1, 2, 3, and each one has 1 leader. And for the default load balancer in Yugabyte will try to place the leader of every tablet in its own node so that you get the maximum use of the CPUs in your entire system. And when now a user sends a select query from the client to our Postgres layer, Postgres will then fetch the individual rows from each leader of the tablets in DocDB. In this case, it needs the row from T1 and T3. So it's going to T1 on node 1 and T3 on node 3. Once they return back to Postgres, it'll do some more massaging of the data or some more processing and return back to the client. Similarly, for the insert path, the insert into table comes into the Postgres, from which it goes to the leader for tablet. And from the leader, it gets replicated to both of its peers. And it's quorum committed. So with 3 nodes, we need a quorum of 2. So as soon as one of the nodes returns back to it, the leader will go back to Postgres and we return back success to the user. So this is great to make things fault tolerant, but to make our database truly region tolerant, like tolerant to outages of an entire region, you don't want to place each of these nodes in a totally different region. So that way, if an entire region, Texas or Florida goes down, you have other regions to take over the load and your database is still available. And this is great from like a availability standpoint, but when we look at regions, there's like a real life like network latency between the regions and the theoretical limit. And there's like AWS East US 1 and 2 has like 12 milliseconds, and US West from the east is more than 50 milliseconds. And I have a small animation to show how slow things can get. And in this one, so we have a user sitting in East US 1 who's trying to turn this white tablet with the leader in East US 1 and write an orange data in that, and take a yellow tablet with the leader in East US 2 and write a purple data to it. And the request goes from the user to the leader, And as soon as it hits the reader, it has to now get replicated to its peers. And you can see that as soon as right now, we already have 2 oranges and this purple, we have 2 of them, but the second one is still returning back to the leader to say it has succeeded with the write, after which it has to go back to the user. So the orange is going to come back to the user first, and then the purple. So in this setup, ideally we want all the leaders to be sitting in east-west-1 closer to the user, so that the latency is like minimal, the queries complete faster. Even if the user isn't exactly in east-west-1, but it's close enough, it's better to have leaders in one zone, because when you're doing more complicated queries like joins of using indexes, the query layer, Postgres, would have to do multiple round trips to the readers to get index rows and the base rows back. So usually you want all the leaders to be in one zone.
So Hari, I think I just wanted to call out a few points that you made in the animation. So one is like, okay, in your setup, looks like you're showing a 3-region deployment, right?
Right.
And by default, if nothing else is done, then leaders of tablets can get sprayed. So some leaders could be like in your example, you have some leader tablets in US East 1, some leader tablets in US East 2, right? Because that's
Right.
the default setting. And you're
Right.
illustrating the point that if you use the default setting, then there is a trade-off, because if your app, suppose, is primarily coming from US East 1, then depending upon where the row sits, there are extra hops, because not just wrapped replication needs to happen, but the app has to kind of get to the leader itself, right?
The leader impact. Yeah.
Yeah, thank you. So I'm sure you're going to talk about like strategies to avoid depending upon use case and fit.
Right. Yeah. Depending upon use case. If you have like users all over, and like you would like want the leaders to be in every region too, because you're using up all the CPUs that you have. But if you are like users are only in one region, and your primary motive is to have multiple regions for like fault tolerance, then we can really go and optimize it much further. I'll just keep the animation. And the latencies between the regions are like, in this example is 50, but depending on your like how far away they are, they could go up to like 400 milliseconds or even more. And like it's, especially if it's like like in our case where it's like on 2 ends of the country, it's going to become very slow. So one of the simplest thing we can do is at universe creation time, we can just set here, pick one of the regions and select the preference for the region. And every leader for our entire universe is going to be in that one region. The region can have multiple nodes. And if they have more than one node, they will be evenly spread across the nodes, the same region, but they will be in this one region alone. Or you can use our YB-admin command and have even more fine-grained control. And we set a secondary zone. And the secondary tertiary zones, what they say is if the primary zone, in our case is just one, is down, what do we do? So if it's just 1A goes down, we don't want to do random to west and east 2 again. We want to pick east 2. So in this example here, I'm saying, hey, prefer east just 1A, but if east just 1 is down, then go to east 2. And this is at the universe level. So every table you create, every tablet index, even the system tables, YB master, they'll all like use this setting. But you can get even more fine grained to the preference, right? And you can use the Postgres table space syntax, and if you create a table space that sets for this particular table space, how many replicas you want, what regions you want it in, and what is the leader preference for this particular table space. And table spaces can be applied to an entire table, an index, or a partition of a table. And doing it on a partition gives you a row level preference. So you can literally say for this table, I want rows ABC in East just 1 and CDE in East 2. And even though it's the same table, if you have users who are querying subsets of the table, then they'll be in the users zones and be much faster. I have one example of a table space here, which sets east 1 to preference 1 and east 2 to the preference 2. I'm not setting anything on west 1 because if both of them are down, then we don't have any quorum anymore. So we'll have to wait for all of them to come back up. And using this syntax, you can create a table and very easily just say, hey, for this table, I want this preference. And similarly for an index, I want to do that. Down here, we have a more complicated partition of a transactions table. And we're saying for European, this example says EU, but for some set of rows, you want the leaders to be in this table space.
So basically within this, so aside from being able to set a preference region for the leaders at the cluster level, you're showing how we can do it at a finer grained basis using the table space concept, right? Because maybe some set of tables, the app is primarily coming from maybe region A and vice versa, right? For some other set of tables. And yeah, I think this point is worth reiterating also. If your preferred region is down, rather than the remaining regions have a random spray of leader distribution, this gives you an ordered sequence of your options. You can say, hey, this is the next region I prefer. And I think usually one good practice here might be in a multi-region deployment to pick at least 2 out of those 3 regions to be somewhat near each other. Still far enough away that they are DR safe, but maybe not like East Coast and West Coast 70 milliseconds. Like the ideal might be have 2 regions which are maybe 10 milliseconds away, and then the third region could be much further out, right? And then you make the 2 nearby regions your option 1 and option 2 for the fallback.
Right.
Yeah. Thanks, Hari.
Thanks. And to show this fact, I have a demo. So let's get that. And I have a universe here where I have 3 nodes, the same setup as we showed before, with east 1, east 2, and west 1. And east 1 by default has the universe level preference. So all my leaders are here right now. And I'm going to create a couple of table spaces and some tables and indexes, and we're going to run a sample app. So let me start that and show what I'm doing here. So I have 3 table spaces to show all 3 combinations that you can do. One is no preference. It just says I want 1 replica in each zone, and I don't really care where the leaders are. Just play them across evenly. The second one says create only a preferred leader. Don't give it a secondary. Just give it a primary. And if the primary is down, use random preferencing. The third one will have both the primary and the secondary. And a sample app is a secondary index app. So it's a simple table with just a key value and an index on the value. So it's going to insert a couple of rows with the key value and then try to read back from the table with the filter on the value itself. So it's going to go to the index first and then the base row. So the read has to go read both. And similarly, the write has to also write in both places. And for a table with random placement, I'm saying the base table, don't give any preference. Index, maybe give a preference of east 1. And then have another table with the proper preference saying, okay, for both this index and the table, set a proper primary and a secondary zone. And let me go ahead and start the app itself. And you can see how the latency is coming to play. So my app is also here sitting in east 1. And give it a few seconds to get started and show the average numbers. Yeah. So this is the table with preference. So actually, we can go look at this view here. And you can see a table with preference has all of its leaders sitting in 203. 203 is east 1. 59 is east 2. And so both the table with preference and the index with preference are going to be in east 1. And my index that only had a primary preference is going to be sitting in east 1. The table with no preference at all It's just like evenly spread across. It has 1 leader in each zone. And my sample app, the one that is reading with preference, is getting 0.6 milliseconds on the reads. And the writes are getting 33, 34 milliseconds. That's because the RAF core.
Could you make the font a little bigger if possible? Thank you.
Can you see that? Okay.
Yeah.
So the writes are getting 33 milliseconds because it's doing a quorum commit of 2 tables. One is the base table and the index table. So it's like 12 milliseconds each. And one without preference, though, reads are at 22, 25 milliseconds, and writes are at 80 milliseconds. So it's like 4x slower in this example right here. Right, almost 4x slower. And what I'm going to do next is, this is the base case, right? So next I'm going to simulate a failure, show that even in a failure, the table with preferences cannot perform the table without any preference at all. So I'm going to simulate the node going down. So I just killed node E on east 1. So as soon as I do that, all the leaders from east 1 are like gone away. And for the table with preference, you can see that the leaders are all in 59, which was east 2.
Because that was your second choice.
Second, right. So for the table with preference, I'd set my second choice, leader 2, as east 2. So they just went to east 2. And the other ones, they never had any, either they had no primary or they had no secondary choices. So both of those are just going to get evenly distributed across west and east. So I'm going to go back to my app and like make it point to my region is down. So I can't like query this region anymore. So I'm going to query the other region. Give it a few seconds again to get the averages right. So this is the one with preference. So the one with preference is getting, we'll give it another couple of seconds to average out again, 17 milliseconds, which is more than like what like 0.6 that we were seeing before, but it's still like fast enough. The writes are getting 150 milliseconds. And then if you go to our table without any.
And one reason for that is among the 2 nearby regions, one of the region is down. So now quorum itself has to go east coast, west coast.
East to west coast.
And you have indexes on the table. So it's like
double writes.
Multiple writes. Yeah.
Right. Yeah. And the one without any preference, the reads are like 80 milliseconds and the write are like 180 milliseconds. So off the bat, this is just going to be like way slower than compared to this one. And if we bring the initial one back, when the initial region does come back, things will fall back in place. So just bring it back and give the load balancer a few seconds, and oh, it's done. The one with preference, as soon as I do that, hop back to 203. And similarly, the other 2 ones, one of them hop back here, and the third one got evenly spread out. And my workload will also now get much faster with the writes. The write is now only like 50 milliseconds and not the 150, because we're not going to US West for the quorum anymore. Cool. And I think, yeah, ready to answer any questions that come up?
Yeah, I think one area we can, I think might be good to deeper dive is like, at the end of the day, let's call out a few reasons why in a multi-region deployment, right? In a multi-region deployment, generally we recommend picking one region as a preferred region and then having a fallback option, right? And Google Spanner, for example, does the same thing. But if we try to distill down to why, it has to do with, number one, if you have a natural choice of where your app is coming from, in terms of improving latencies, having the leader tablets be near that app. That is a simple thing to understand. Second is some operations are not simple key value like lookups, right? I mean, in a traditional database, you have all kinds of operations. If it's like a single shard operation, like a read or write, the overheads are still low. But the moment you start involving multi-shard operations, multi-shard transactions, there is leader to leader communication that happens, and in which case it makes sense to co-locate all the leaders of tables in a single region if latency is very important, correct? But I think an obvious question is, hey, there must be a catch. Like, am I not losing something by co-locating all the leaders, right? And that might be what are some pros and cons, Hari? Like, is there a disadvantage of setting all the leaders in the same region?
Right, mainly the resource consumption, right? Because everything you're using your entire CPU. I think if you go look at our metrics here, and if you go look at the node level metrics, it's going to show up that all of my writes are going to one node, and all my CPU usage. It's like I mean, my query here isn't like to create.
Yeah, your workload is not too intense right
yeah,
now. To highlight the
right
point.
now. Right, but it's only going to use 30% of my entire CPU because I have like 2 other nodes that are just sitting there as a fallback and not really using the CPUs that much,
Exactly.
right? I'm using the disk, but not the CPU. So that's definitely one like a drawback.
Yeah,
Because you're paying for it.
Yeah, like one simple example to illustrate the point is, let's say you have a 3-region cluster and you have all the leaders in region A. And suppose, let's just say you have a read heavy workload, right? And you're doing strongly consistent reads, then pretty much, at least in a write heavy workload, then you're replicating data to all 3 regions, other regions somewhat busy. But like in a read heavy workload, doing strongly consistent reads, then only the leader nodes are busy. So in some sense, there is a resource versus latency trade-off here. If the higher latencies are acceptable, then by all means, don't use this feature. Just have your leaders spread out, right? And you're utilizing the CPU resources of all nodes across all regions. But if you want to really tune for latency, then this is a very good technique to optimize for latency. Yes, it comes with the trade-off that then you're not utilizing as much the resources in other regions, but it is still an active region, and it's available to take over within like you showed, within a matter of seconds to keep the system up and running. So I think that's the trade-off. Some things to keep in mind. You can still do follower reads, which is like from YSQL and YCQL, both our APIs offer ability to read from followers. So in some applications, it might be perfectly acceptable to read data that is just like few seconds behind from other regions itself. So then that is one thing to keep in mind. I think there's one question. Say West goes down for a day, then comes back online. Given the East regions were preferred, will West be updated? In your examples, you had East 1 and East 2 as the first 2 choices, and West going down should not actually cause an impact, right?
Yep, it will not cause an impact. And will it be updated? Yes, West will be updated. Once it does come back, it'll we will send all the log from the East regions over to West, and we'll get it updated.
Exactly. Like, I mean, if a region is down, it comes back, it'll catch up from the source of truth, the leaders. So that is almost even independent of this feature itself, right? I mean, that is by design. Even in a single region cluster with multi-zone, if one zone is down for a day, when it comes back up, it'll heal itself and so on. So that applies in the multi-region deployment also. But in fact, West going down will be actually a good failure scenario compared to East 1 or East 2 going down, because in Hari's examples, the leaders were either on East 1 and as a second choice on East 2, something like that. Wonderful. So thank you all for joining us, and we'll see you next week. I don't know. I think one of the weeks, if it's we run into the Thanksgiving week, but we'll confirm. We'll keep posted on LinkedIn when the next episode is. And thanks all for joining and for the questions. Hari, over to you for closing thoughts.
Thank you, Kannan. Yeah, thanks everyone for joining. And I think we have talks about this online. And you can always ask us questions on Slack, and we'll be able to answer you any of that.